This is Jack Jackson. We're going to be looking today at Cartesian graphs of the 6 basic trigonometric functions. And and once again, as often, we're going to be using my sketch Trigonometry Ultimate. And if you remember in our last video, we looked at this sketch, which had a lot of stuff on it, showing how we got from a unit circle representation to a Cartesian graph representation of our trig functions. So this next page, called Basic Trig Graphs, shows all the basic graphs of the trig functions. And we're going to start with the sine graph there and look at it. The function is g of x equals sine of x. And we're going to see some of the properties that this function has. Well, a couple things you may notice is that it is defined for all real numbers. So the domain is all real numbers. We notice that the range goes from -1 to 1. It does include -1 and 1 and all the values in between, but does not go above or below -1 for the y values. So let's just show some of the properties here of this function. Okay, so once again, the domain is all reals from negative infinity to infinity. The range is from -1 to 1, including that. The period is 2 pi, and the way you see that is as we go here. Let's put a point on here, and we notice that as we go from here from 0 to 2 pi, we go through one tracing of this whole basic shape, and that it repeats the exact same shape as we go from 2 pi to 4 pi. Of course, we see that in the unit circle representation as we go around the circle here, it's just repeating. As you go around the circle once, it goes through the pattern, but as we go around the circle again, we're going through the same pattern. So this has a repeating pattern over and over and over and over and over again. So this is what we call by a periodic function. So its period is 2 pi. So if we were to shift this by 2 pi, we would get the left or right, we would get exactly the same graph. Notice that this one does go through the origin, so the y-intercept is 0, 0, and it has some x-intercepts, which are also periodic. They happen here at 0, at pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, at -pi, -2 pi, -3 pi. So if you look, that's all integer multiples of pi. And of course the x-intercepts will have a y of 0, and so they look like n times pi for the x-coordinate, and the y-coordinate is 0, such that n could be any integer. So if n is 0, that's right here at the origin. If n is 1, that's pi comma 0, that's right here. If n is 2, that's 2 pi comma 0, that's right here where it crosses the axis. If n is 3, it's 3 pi, 4 pi for n is 4, n is -1, that's -pi comma 0, and so forth. It turns out all these points where it hits the x-axis are actually inflection points as well, and so we notice that when y is positive, when it's above the x-axis, the graph is concave down, and when the graph is below the x-axis, when y is negative, then it's concave up. And remember, an inflection point in general is a point where it changes concavity. Concave down means like an upside down bowl or an umbrella, whereas a right side up bowl would be concave up. So it switches from concave, say right here from -pi to 0, it's concave up. From 0 to pi, it's concave down. From pi to 2 pi, it's concave up, and so forth. It has maxima. All these maximum values have a y of 1, so the maximum y is 1. Where does that occur on the x? Well, it occurs at pi over 2, and then multiples shifts of that by the period of 2 pi. So it's pi over 2 plus 2n pi, such that n is an integer for the x, and of course y is 1. What about the minima? The minima occur here for one place at -pi over 2, and then shifts of that by 2 pi. So you shift to the right by 2 pi, you get 3 pi over 2, and another right 2 pi, you get 7 pi over 2 for x. If we were taking the -pi over 2 and shift to the left by 2 pi, we'd be at -5 pi over 2. and so forth. So this gives us all the different possibilities. You need to get used to this notation, because this is a compact way of saying and listing this infinitely many points in this set. So we're thinking of the points, whether they're x-intercepts, y-intercepts, inflection points, minima, maxima, whatever, as points on the graph, so they have ordered pairs, and we can see what they are. So we list them as with parentheses and a comma, and then, but notice that we have a formula for the x-coordinate here, such that n is any integer. Notice this does not have any vertical asymptotes, or any kind of asymptotes at all, and of course we're going to see that some of the functions do have asymptotes. We get some identities from the unit circle. Remember, if we have two points here that are, let's do this. Where's my control? If we look at some point here, and they look at its opposite down here, so a positive value here, and then its opposite over here, they're going to, over here on the unit circle, they're going to have the same x but opposite y's. So they'll have opposite x's, but the same opposite angles. So over here, theta and minus theta, and over here that would be x and minus x, but they have the same y values. So that over here on the they have opposite y values, excuse me, over here on the unit circle. So they're going to have opposite values over here. So in other words, the sine of minus x is the opposite of sine of x. Now, how does that play out here on the graph? Well, on the graph, that shows that if you go here, and if you got a point xy on the graph, you've got its corresponding point over here, which is negative x, negative y. So that means if we could take this thing and actually rotate this 180 degrees around the origin, the graph is going to look the same way. And so you're going to see the same looking graph if you rotate it 180 degrees around the origin. We call that an odd function. Now, what about the symmetry from the graph when you look at over here in the unit circle? If you look at supplementary angles, so if you're looking at, say, an angle here in the first quadrant over here on the unit circle, and then a corresponding angle with the same reference angle in the second quadrant, they're going to have the same y value, but the angles, one of them is going to be theta, the other one will be pi minus theta. So over here on the unit circle, one's going to be x, and the other one's going to be pi minus x, and so those give you the same size angles, same y, not the same size angle, but the same y. They're supplementary angles. So we get sine of pi minus x equals the sine of x. And then on the unit circle, if we have pi plus x, that's an opposite facing angle. So if we look at, say, we go to here, some value of x, then we do pi plus that, we've gone over to here, and pi plus that gives you an opposite facing angle over here on the unit circle. Over here, what that gives you is a shift by pi, and when you do that, you get the opposite value of the y. You get opposite y's there, both on both graphs. So sine of pi plus x is the opposite of the sine of x, and you can see that. So here you can see anytime you shift this to the right by pi, or left, right or left by pi, you're going to get the opposite y. So that if you take a point here and you shift it to the right by pi, then you need to flip it over the x-axis to find the point there. So some nice little representations of sine of x, and we see its basic properties.